So, welcome to Chapter 6. We're going to continue the discussion that we started in Chapter 5 with discrete probability distributions, and now talk about continuous probability distributions. So as we discussed in Chapter 5, random variables may be discrete or continuous. So a discrete variable is one that is countable. It has a finite number of distinct options. So we looked at the example where we were trying to determine the number of people that would visit a Starbucks during a 5-day week. That's a discrete variable. We can count the number of people. Whereas continuous variables are infinite. We can't count them. It could be something such as the amount of time that has passed. Now we may say, well, we can measure time down to seconds. Yes, but it can get down to milliseconds and fractions of a second and fractions of a millisecond. So technically it is a continuous variable. It's got an infinite number of possibilities. Now, a lot of times we may treat continuous variables as discrete variables, but technically they are still continuous variables. If we're calculating returns on an investment, I mean, yeah, we can say money goes to 2 decimal places, but we know that we're rounding to 2 decimal places. So if we have to round it, then it's really a continuous variable, not a discrete variable. So when we are looking at continuous variables, the probability that any random variable equals a specific discrete countable number is 0 technically. I mean, it's immeasurable. So since we can't assign a non-zero probability, then and those would not all sum to 1, we really can't calculate the probability of exactly one variable. But what we can do is calculate a probability for a range. So we could say that the probability of X is greater than or equal to the probability of A, or less than or equal to the probability of B, where A and B are our upper and lower limits in our range. So for those of you who have taken calculus or who remember your calculus, this should look very familiar. We're going to start talking about functions. And so then we talk about integrals. Now, thankfully, we're not going to get into that level of calculus here where we're doing integrals right now and functions. But this is where we're headed. This is why these two are interrelated and why that's a prerequisite for this course. So we're going to use the probability density function to find the probability that a variable assumes a certain value within an interval. So the cumulative distribution function, is what we use for, again, a continuous random variable. So we'll say that the function is equal to the probability that our random variable is less than or equal to a certain value. So we can say the probability that a variable is greater than or equal to A and less than or equal to B, remember those are upper and lower limits, is the probability, is the function of B minus the function of A. So when we're talking about a continuous distribution, it's easiest if we are looking at what's called a uniform distribution. So a uniform distribution is when every underlying random variable has an equally likely chance of assuming a certain value. So the example that was given is, you have a repair person coming to your house. You've been given a range of they'll be there between 2 and 3. What's the probability that they're going to show up between 2 and 3? Well, hopefully it's 1. It's 100% that they'll be there in that range. Now, we all know, I think if we've had repair people come to our house, that's not entirely true, but let's say it's true for this. So what's the probability that they're going to show up at between 2 and 2:30? Well, there's a 50% probability. And then there's a 50% probability that they'll show up between 2:30 and 3. So the probability of them showing up any time between 2 and 3 is equal, right? There's no higher probability that they're going to show up closer to 2 or a higher probability that they're going to show up closer to 3. So anywhere in there is an equally likely probability. So for a random continuous random variable, again, we're looking at that function where our upper and lower limits are a and b, and so then that probability is going to be somewhere between 0 and 1 over b minus a, the upper limit minus the lower limit. So let's walk through an example to make this make more sense. Now, before we get there, let's talk about our values that we need to know. So the expected value, or the mean, is a plus b, so the lower limit plus the upper limit, divided by 2. And then the standard deviation is the square root of b minus a, upper limit minus lower limit, squared, divided by 12. Now, one thing to notice, it is always a 12, okay? Always a 12. I'll be honest, I don't know why it's always a 12, but it's always a 12. That denominator never changes. Remember your order of operations also. So you want to subtract the upper minus lower limit, then square that, then divide by 12, then take the square root. So make sure we're following our order of operations. All right, so let's look at, here we have our a and b. These are our lower and our upper limit. So a is our lower limit, b is our upper limit. So if we're graphing this, x is our horizontal axis and y is the function of x, okay? So we've graphed our lower limit a and our upper limit b. Now, the height of the distribution isn't necessarily a representative of the probability, but the height is 1 over b minus a. So 1 divided by the upper limit minus the lower limit. So you see that this really creates a triangle here. And so we can calculate, of course, not a triangle, a rectangle. Goodness gracious. So we can calculate the area of a rectangle as base times height, right? So we can find the probability that a certain falls under a certain range as the base times the height. So, for example, we're told that sales for a particular cosmetic line follow a uniform distribution. They have a lower limit of 2,500 and an upper limit of 5,000. So first of all, let's calculate the mean and the standard deviation. So if our lower limit is 2,500 and our upper limit is the 5,000, remember the mean is just the lower plus the upper divided by 2. So that is 2,500 plus 5,000 divided by 2, or 3,750 is our mean. So then our standard deviation, and again, I encourage you, pause the video, you have the formula, practice calculating this, then start the video and check your answer. So the standard deviation is the upper limit of 5,000 minus the lower limit of 2,500. Square that, divide by 12, then take the square root, and we get $721.69. $721.69. So we're asked, what is the probability that the sales exceed $4,000? Okay, so what's the probability that X falls between 4,000 and 5,000? So we know now that our formula is base times height. The probability is base times height. In this case, my base is the difference between 5,000 and 4,000. So my base is just 1,000 here. And my height, remember, is 1 divided by b minus a. Now in this formula, we're going to keep our original upper and lower limits, okay? So we're going to take the 5,000 minus the 2,500. 1 divided by that 2,500 gives me 0.0004. So we can say that the probability that sales exceed 4,000, which means that sales fall between 4 and 5,000, is 1,000, our base, times 0.0004, our height, or 40%. Now we can also calculate what is the probability that sales fall between $3,200 and $3,800. So in this case, what's the probability that X is greater than or equal to 3,200 and less than or equal to 3,800? And that, of course, is base times height. So now my base is going to be the 3,800 minus the 3,200, or 600. Our height we already calculated. Remember, it's that 1 divided by the upper limit minus the lower limit, which was 0.0004. So now I can say 600 times 0.0004 tells me that there is a 24% probability that sales will fall between $3,200 and $3,800.